number 7 here. Two spheres of two different masses are separated by a distance of this. Calculate the magnitude of the gravitational forces, and then what if the force between the spheres is now this? How far apart are their centers? So, what do we expect these forces to be the same or different? These two that in A that they asked for. Force on A by B and the force on B by A. What do we expect? Same or different? Same. Exactly the same. I'm sorry, we should have our rubric open. Let's see. Because, remember this, since this one mentions force, we need to pay attention to this rubric when we're thinking about our why and our how, because we're going to be required a force diagram to show our understanding here. So here we are, number 7. I would start off with the forces in A are the same magnitude. What about these objects are creating this force? The mass, yep. The mass of the objects create the force. Create the forces. What else helps control how the size and the magnitude of these forces? Distance. I'm going to take contribute to the forces, the magnitude. And you could write in there also the fact that these the forces are always attractive. But I think if you show that here in your diagram, where you've got A and you've got B, and you show that the forces between these are towards each other, you know, the force of gravity on A due to B, and the force of gravity on B due to A. I think if you show that those two are pointing towards each other, that's fine without having to state it there in words. Are we good on the why? Oh, I forgot to walk around and check your whys. I'll come around and check after this problem. I knew I forgot something this morning. So equation-wise, we want to use our universal gravitational equation, which is this one right here. All right, and we're looking for f sub g, so they're equals of f gab equals big G, which if we look on our equation sheet is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared over, and I think I should move all of that over here. Find more room, there we go. For me, let's see, M1, 9 and 9.3 and 0.65. So I have 9 kilograms, 9.3 kilograms, and 0.65 meters squared. And now it's just plugging in those values and coming up with your answer. For part B, they tell us the F and they don't tell us the R, and so it's just rearranging it to find R instead of finding F. So let me know if you need help with that math individually. I'm going to come around and check your Y's. I forgot. All right, so we're going to jump into number 3. Again, we do have forces, and you know the Y here is very, very similar to the last one we just did. You know that their masses create this gravitational attraction between them. It's tempered by the forces that the distance they are apart, and even the fact that it would be the same force diagram. So the Y for number 7 that we did, just because it's Friday, translate that into number 3, and it's the exact same understanding. So C number 7. Mathematically, it's going to start off the same, and the math gets a little not convoluted, but so we're going to grab this, grab our same equation again. All right, and the one difference we're told about the relationship between the masses that M1 plus M2 equals 4 kilograms. Right? Yes? I think that's true for everyone. So I rearranged this so I had M1 equals 4 kilograms minus M2. Now I can substitute in, let's see, they tell me the force and the distance. So I'm back here substituting in now 3.3 in my head times 10 to the minus 10 newtons equals, you'd think I would learn by this point to start from the edge, equals 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. M1 and M2 over 0.31 squared. Let me just double check that one here. Meters. And now the two equations, I have now two equations, this one and this one, with the same two unknowns. And so mathematically, algebraically, what I would do is take the one equation, my M1 equals 4 minus M2, substitute that in my second equation for M1, and then I only have one variable and one equation, and I can work it down until I get M2. And that's a lot of fun algebra to do. Yeah, you know, it's a good way to spend an afternoon. Well, or 5 minutes of an afternoon. What I would suggest is, hey, use your tools. Do you guys understand about two equations and how to substitute in and algebraically solve? Yeah. So let's use our tools instead. Because we know the theory, we know how to do it. And so I'm going to grab Wolfram from our site, from our main site here, and I'm going to put in the two equations. And I'm going to call them X and Y rather than M1 and M2. Alright, so I'm going to put in X plus Y equals 4. Let me make this bigger so you can see what I'm typing. X plus Y equals 4, comma, space. And now I need to put in my second start equation here. And so, let's see. 3.3 3 e to the negative 10th equals 6.67 e to the negative 11th times, this is xy divided by 0.31 squared. I think that's right. I'm just going to keep double checking here. And when I hit equals, hopefully, it chugs away for a second and then comes up. So, 1, 2, 3, 0.387. So those two come out to be my solutions. And okay, they add up to 4, so that's happy. If you need help putting that in, or if you want to do it algebraically, let me know, and I'll come over and help you. I'm going to just double check my solution. All right, so we're going to try to stick number 4 in here before the end of the block. We've got these 4 spheres located at the corners of the square, and so the so my y would be things like every sphere is gravitationally attracted to every other sphere. And the amount of attraction is controlled by the mass and distance. And then, of course, since it mentions forces, I need to include a force diagram. I'm going to think about doing this one for the upper left sphere. So I'm going to put a sphere here, 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 and here. And so this, we'll call this sphere 1, 2, 3, and 4. So 1 is attracted to 2. 1 is attracted to 4. And 1 is attracted to 3. In that format. So, they all have the same mass, right? True. 9.5, 0.7, so my M is 9.5 kilograms. The length of the side of my square, which I'm going to call S, for me is 0.7 meters, I believe. Yes. And it doesn't matter which one I do here because they're all going to be in the same situation. Now, this could be a much trickier problem if these masses weren't identical, or if they weren't on a square. Same idea, same concept, but mathematically it would just be trickier. Would everyone agree that FG12 equals FG14? right? Same distance, same masses involved. And they're both larger than FG13. Yes? Does that make sense? Geometrically, if I take FG12 and I add it to FG14, the resulting vector, which I'm going to call FG5, would be at a 45-degree angle because they're in the same, these two legs are equal, and it's a right triangle. All that geometry flowing back, right? Freshman year. And then FG13 is in that same direction. So if I can figure out the magnitude of FG5, I can just add that magnitude to the magnitude of FG13 and have my total force, right? So vectorially, once I combine FG12 and FG14, then I know I'm in a straight line and the mathematics becomes a little simpler, right? The vector math. Kellyanne, you have a treat. Look at it. It's good. Just concentrating. All right. So, figure out how big these forces are. So FG12, I'm using my one that we're pretty used to by this point. I'm going to write it over here. F sub G is big G, M1, M2 over R squared. So FG12 would be big G, M times M, which would be M squared, over 0.7 meters squared. So my M is, for me, is 9.5 kilograms. And that should be squared. And I'd figure out FG2. If these sides are 0.7 meters, then this length here is 0.7 meters times the square root of 2. Yes? Yeah. Okay. So when I figure out FG13, I still have big G in there. I still have the same masses, 9.5 kilograms squared, but now the distance between them is 0.7 meters, square root of 2 quantity squared. Kind of interestingly, when I square that, square root of 2 squared is 2. So I don't know if you guys see this, but look at this. FG13 equals 1/2 FG12. Because you have the square root of 2 squared, that's going to make the bottom of this have a 2 in front of it, where up here it didn't have a 2, so it's going to be half as big. Interesting. Maybe just if you're a physicist. I find that intriguing. Now, I need to combine these two, FG12 and FG14, to get the FG5. Oh, wait, that's a 45-45 triangle. 90 triangle, right? So that means, using the same logic I used here, that FG5 equals the square root of 2 times FG12. So my final answer ends up being square root of 2 times FG12 plus 1/2 times FG12. Because of all those triangular relationships. I'm going to pause, but let me know if you need me to come over and talk to